everyone. Today I'm going to talk about the development of electrochemical aptasensor for detection of aflatoxin B1 in cereals. And first, we want to know what are aflatoxins. Aflatoxins are common food contaminants produced by molds. The molds which look like these beautiful flowers under the microscope, but they can contaminate a wide range of food and feed products. Imagine this morning when you were having breakfast with your family, what never crossed your mind is that everything on your breakfast table can be contaminated with aflatoxins, from cereals to milk and eggs. And the most toxic type of aflatoxins, aflatoxin B1, get oxidized in the liver, producing DNA adducts, and these DNA adducts can lead to development of liver cancer. And that's why many countries, including the EU, set a strict regulation to limit the amount of aflatoxin B1 in food and feed products, which is as low as 2 microgram per kilogram for aflatoxin B1 in corn. This is one of the lowest limits of any food contaminants, and that's why it's very important to have sensitive and quantitative methods for detection of aflatoxin B1 in food samples. So during my PhD projects working on aflatoxin B1 testing, I did an interview with a local magazine here in Switzerland, Graubünden Woche, and after a few days, we received this picture from one of the readers, a woman named Cornelia. And this is a moldy lid of an apricot conserve, and she was interested to know if the apricots are contaminated with aflatoxin or not. And the way that this test can be done today is to send the sample to a central laboratory, and the test is done by experts using HPLC mass spectrometers. And this whole process is time-consuming and expensive. But what is needed by farmers, food inspectors, and also concerned consumers like Cornelia is a portable device capable of on-site detection of food contaminants such as aflatoxin B1. So for this purpose, we proposed using an electrochemical aptasensor combined to a smartphone. And this device can consist of 3 main parts. The biorecognition is an aptamer, which specifically binds to aflatoxin B1 in the food. The transducer converts this binding into a current signal. The transducer consists of screen-printed electrodes connected to the measurements device called potentiostat. Here you see as the gray box. And as you see in the picture, both screen-printed electrodes and potentiostat are already miniatures, small and portable. More interesting is that the potentiostat can be connected to a smartphone via Bluetooth or USB, and then the smartphone, as the readout, can show the results to the user of the results of the test. So to develop the aptasensor, we used a previously reported aflatoxin B1 aptamer, and here we tested 3 truncated sequences of this aptamer. It's a DNA aptamer, and we modified these sequences with these truncated sequences with the tile group at 5' end, and a methylene blue group, which is an electrochemical probe at the 3' end. Here you see the aptasensor working principle. So we immobilize the aptamer sequence on a gold electrode surface through the tile group, and then we apply potential to the electrode and measure the current generated by the redox reaction of methylene blue. After binding of the aptamer with aflatoxin B1, the conformational change of the aptamer increased distance between methylene blue and the gold electrode, and decreasing the electron transfer rate, which result in a decrease in the redox current generated by methylene blue. This decrease in the current is proportional to aflatoxin B1 concentration in the food sample. This approach is, the main advantage of this approach is that it provides a single-step reagent detection because we already have the methylene blue and the electrode during the fabrication of the sensor, and we don't need to add any reagents afterwards. So based on previous studies of the similar aptasensing approaches, we hypothesized that between these three truncated sequences, the one with a more destabilized structure may result in a higher signal chain upon binding. And we predicted the secondary structure of the truncated sequences with Lupak software, and that identified that truncate 3 has the most destabilized structure, and then expected to produce a higher signal change after binding with aflatoxin B1. So we moved on with the electrochemical measurements. For electrochemical measurements, we used a square wave voltammetry, which is specifically more suitable for this aptasensing approach. In a square wave voltammetry, we apply an square wave potential to the electrode. Here we measure the current at the end of forward and reverse pulses. So as you can see in the current time window, after each pulse, the current decays, and the rate of this decay depends on the electron transfer rate. And in our aptasensing approach, we're interested to measure the difference between electron transfer rate before and after binding. So this is the main reason that we use this electrochemical method for the electrochemical measurements of the aptasensor. Also, in the square wave voltammetry, the current that is measured is the difference between the forward and reverse currents. So because these two forward and reverse currents, they have opposite signs, so it produces a higher current and a higher signal, which helps to increase the signal to noise ratio of the sensor. And for the square wave voltammetry measurements, as you've seen in the previous slide, the frequency is one of the most important parameters that can affect the aptasensor signal. So we optimize the frequency, and here we prepare the aptasensors using a different concentration of the aptamer of 100, 500, and 1000 nanomolar. Then we measure the signal change upon binding of these aptasensors to aflatoxin B1 over a frequency range of 10 to 1000 hertz. And we observed that we observed a negative signal change or a signal off mechanism for all of these three truncated sequences over the frequency, over all the measured frequencies, which indicates that we had a more rigid structure after binding. The aptamer had a more rigid structure after binding to aflatoxin B1. Also, we obtained the highest signal change at the lowest frequency that we use, 10 hertz, for all three truncated sequences. And from now on, we use the 10 hertz, the lowest frequency, as the optimum frequency for the measurements. We also optimize the aptamer density, which can affect the aptamer signal. And here we compared the maximum signal change at different concentration of the aptamer and the electrode of 100, 500, and 1000 nanomolar. And we obtained the highest signal change using truncate 3 at 500 nanomolar, confirming our hypothesis that truncate 3 with a more destabilized structure produces a highest signal change between these two truncate sequences after binding with aflatoxin B1. So we move down to real sample analysis. For real sample analysis, we follow the simple extraction procedure, which only takes 15 minutes. And after grinding the samples and extracting the 80% methanol solution, we just did a simple filtration and dilution. And then we use the extract for real sample analysis with no need for further cleanup. We use the aptasensor with the optimum parameters for detection of aflatoxin B1 in buffer and corn extracts. Here you see the calibration curves, and as the aflatoxin B1 concentration increases, the negative signal change increases as well. increases as well. And then we obtained the limit of detection of 1 picogram per milliliter, both in buffer and extract. However, most importantly, the linear range of the active sensor, both in buffer and extract, covered the EU limit of 2 microgram per kilogram, which corresponds to 100 picogram per milliliter after its extraction. So this shows that we were able to detect aflatoxin B1 at the EU limit of 2 microgram per kilogram in extract, in corn extract. So to summarize here, we successfully developed an aptasensor which provides one-step reagentless detection of aflatoxin B1 at the EU limit of 2 microgram per kilogram and with a low limit of detection of 1 kilogram per milliliter. The next step would be to integrate this after-sensing platform into a portable device and using the smartphone for point-of-need food safety testing and point-of-need testing of aflatoxin B1. And then I would like to thank my collaborators at CCM Landcard, Laboratory of Toxicology at ETH Zurich, and Nanobiotechnology for Diagnostic Group in Barcelona. Thank you for your attention.